So let's get started with class. Today's just going to be an exam review day. So I'm just going to cover whatever questions you have regarding the exam review that I posted last Wednesday. So you can find what I'm covering today on the Canvas page. And this is the best resource to understand for being able to do the exam. Generally, if you understand how to do the problems on the exam review, like you'll be fine on the exam. The problems on the exam won't be like more difficult than the ones on the review. And I'm not going to be pulling from material that's not on the review. So if you can do the review, as well as like problems that are similar to the problems on the review, then you should be fine with the exam. I guess before taking questions, I can talk about the exam a little bit. So you should already know, like the sections covered are 5.7 to 5.8, chapter 6, and then section 7.1 and 7.2. So you can kind of like, you should be able to predict what kinds of problems are going to show up. Like there's going to be one problem where you have to find like an area between curves. There'll be a problem where you have to find like, you have to set up a volume integral by looking at like the area of a cross section. There's like three main shapes we looked at. We looked at like a pyramid, a cone, and like a pyramid or a cone with like an ellipse base. So like you should expect you have to do like similar triangles. There's going to be like volumes of rotation or regions of rotation, right, to find the volumes, like disc washer, shell method. And then there'll be like a spring problem. So it's like 5 of the problems right there. And then there'll be some like integration by parts and like trigonometric integrals. So it's going to sound like a lot, but there's 11 problems, but 5 of them are just computing integrals, which should be pretty quick. Like there'll be like 5 of the problems are problems that are similar to like what's found here. So those should go pretty quickly. And then the other problems should probably take around like 5 minutes or so, give or take. So I gave a similar exam last semester. There wasn't any problems with time. And I think the average was around like a 80% or like 83%. So I don't make like really difficult exams or anything like that. So if you understand the review, like you should be fine with the exam. Okay. Yeah, so I guess I'll take any questions you have. If you have any questions you want me to go over from the review, or if you have like general questions you want to ask as well. Yeah, go ahead.
So general question, but are you going to be posting a executed this?
Yeah, I'll be doing it after class, or like I teach after this one. So, and I plan on sending out the solutions to the group works as well. Questions? Any other questions?
But yeah. Would be like pictures or shapes, or you need to draw them? Or
some of them you'll have to draw. Some of them will be provided. That's what I would say. I'm not going to ask you to do like on the group work yesterday when finding like the area between curves, you had to find like 3 intersection points and you had to draw like 3 curves. It'll be easier than that. Yeah.
Can we get no card for?
Oh yeah, I said that, but I don't have it written on mine. So you can use an index card. You can write like equations or something. Yeah, you're allowed an index card for a reference. We'll go left, right. Yeah, go ahead. I think it can be front and back. Sure. 11. Yeah, but it sounds like a lot. I said this earlier, but it sounds like a lot, but 5 of them are just going to be like evaluate the following integral. So those ones should go pretty quickly. It's Friday. This time, but like during class. Yeah, it'd be too hard to organize another time. And plus, like a lot of people come from off campus, so can't really, you don't want people to do that in the evening. Okay, so yeah, if there are any other general questions, you can ask those. Are there any questions specifically you want me to go over from the exam review? Yeah, and 3. Okay, yeah, so for number 3, it wants you to find the area of the region bounded by the graphs. So we have 3 different curves going on here. So we have y is equal to 8 over x squared. We have y is equal to 8x, and then y is equal to x. So we have this picture right here. And so it wants us to find the area of this shaded region here. And so this is one of those problems that there's kind of like an extra step or like a twist, I suppose, in this one. And that depending on where you're at in the domain, the integral or like the lower bound of your function is going to be, or the upper bound of your function is going to be changing. So if we're on the part of the domain from 0 to 1, then the upper bound is given by 8x. And if you're on the interval from 1 to 2, the upper bound is given by 8 over x squared. And so we'll divide this region to two smaller regions. So this region I'll denote by A1. And then this region I'll denote by A2. And so because we have two upper bounds, that should tell you that there's going to be two integrals that we'll need to set up. There'll be an integral corresponding to A1 and then an integral corresponding to A2. And so A1, in this case, like once you divide it into these two regions, I'll just say like, if you're finding A1 or like this first area, just ignore everything over here. And just think like, how would we find the area between y is equal to 8x and y is equal to x? Well, this is just going to be the integral from 0 to 1, because this goes from 0 to 1. The upper bound is 8x, so this is going to be integral of 8x. And then the lower bound is given by y is equal to x, so it'll be minus x dx. And so this is just the integral of 7x dx from 0 to 1. So that's A1. And then we have that A2 is going to be done similarly. So A2, this corresponds to this area. And so this is the area between the curves y is equal to 8 over x squared and y is equal to x. And we're on the interval from 1 to 2 now. So this is going to be the integral from 1 to 2 of 8 over x squared minus x dx. And so this means the total area. So we found the area of this region with respect to this integral and the area of this region with respect to this integral. So now to find the total area, just add the two integrals together. So the total area, this is equal to A1 plus A2. And so this is really just equal to the integral from 0 to 1 of 7x dx plus the integral from 1 to 2 of 8 times x to the minus 2 power minus x dx. And then you can compute these two integrals. They're pretty straightforward. On the exam, I'm just going to ask you to set up the integral. You don't have to actually compute them because you'll be doing plenty of other integrals. And usually I give you just like polynomials. So like the computation of this isn't really that interesting. So I'll just leave it here. And on the exam, you just have to set it up. But yeah, so this is how the problem is set up, and then you can compute this. Okay, any questions about this example? Yeah, so you just need to be conscious of, like, is your upper bound changing over time? If so, then it usually means that you need to have two integrals. And in the group work yesterday, it was the lower bound that was changing over time. So you had two different integrals, so it's kind of analogous. Okay, any other questions before the next one? Okay, what other problems from the review do people want me to go through? Yeah, Jack. 9. Oh yeah, this one looks weird a little bit, but it isn't too bad once you work through it. So for problem 9, it wants you to find the integral from 2 to 5 of some function g of t dt, and it doesn't tell you what g of t is, but it does tell you that the average value of g on the interval from 2 to 5 is going to be equal to 9. And so in general, we'll do it like this. So in general, like the average value of g on the interval from 2 to 5 is given by the following integral. So this is equal to 1 over 5 minus 2 times the integral from 2 to 5 of g of t dt. Right, so this goes back to, I think it was section 6.2. I think it was the last thing in section 6.2 is where this formula comes from. So the average value of a function on an interval is 1 over the right endpoint minus the left endpoint. And then you just integrate whatever your function is. And so we're told in the problem that this ends up being equal to 9. So the average value of g on this interval is 9. So you set this equal to 9. Let me, I kind of want this to be on a single line. right? So this is equal to 9. And so this is really saying that we have 1/3 times this integral from 2 to 5 gt dt is equal to 9. And this is what we want to solve, right? We want to find what this integral is. So it's just a matter of multiplying both sides by 3. So if you multiply both sides by 3, you get the integral from 2 to 5 gt dt is equal to 27. And so this is the answer. So it's one of those problems where if you can set it up, it isn't so bad, but I think you have to like be able to parse and understand what the question is asking and like how to set things up. Okay, any questions about this problem?
We don't solve it, just
It's solved. Like we have like this is just a number, right? Like a definite integral is just a number. So we found that this number ends up being equal to 27. So there isn't really anything else to say about it. Like we don't solve for g of t because we don't have any information about g of t. There can be like infinitely many functions that satisfy the fact that the average value of g is 9 on this interval. So we don't have enough information to find what g is, but we know what the integral is. Yeah, another question.
did you try this?
6. Oh yeah, this is a good one to know. Yeah, so like the volume equation, we've been looking at like 3 shapes in particular. So there's like 2 cone problems that we've done, one with like a circular base, one where the base is an ellipse. And then we also looked at one where the base is a square, so you get a pyramid. And so for this one, like all of them, they rely on you knowing how to do like the similar triangles trick. So I tell you in the beginning that the area of an ellipse is pi times AB, where A and B are the lengths of the semi-major and semi-minor axes. So you don't have to know what these are necessarily, like they're pictured here below. So if you have an ellipse, it's an oval. So you have 2 different radii. You have like a horizontal radius, and then you have a vertical radius given by B. And so for this one, it wants you to compute the volume of a cone of height 12, whose base is an ellipse with semi-major axis A is equal to 6 and semi-minor axis given by B is equal to 4. So like the B is equal to 4 corresponds to this part here. And then the A being equal to 6 corresponds to this part right here. And so we have 2 different triangles that we have. Like ultimately, to find the volume, this volume is going to be equal to the integral of some area of a cross section, right? So we need to find the area. So what I mean by a sub y, this is the area of the cross section. So we slice this cone, and by slicing the cone, we get a cross section, which is given by this oval. And so what we do to determine like what the area of the cross section is going to be, like the area of this ellipse is going to be pi times AB, where we'll say that this is going to be our B. This green radius here is going to be our B. And then this radius here is going to be our A. And so to determine what A and B are going to be, we're just going to use similar triangles, except now we're going to have 2 triangles instead of 1. So we have this triangle here, whose base is 4, and then the height is going to be 12. Kind of covering up the B a little bit. So this is B. And then we have this other triangle in orange. Let me do a better, it doesn't really matter. You don't have to draw the picture if you don't want to, but I just want to make sure my picture looks nice. Okay, so then we have this other triangle like this. Oh, wait, no, I did it right the first time. So we have this other triangle in orange here. It's kind of hard to draw it without overlapping, but it looks something like this. And then this is, we have this smaller triangle inside of it, which is given by A. Right, and so the goal here is we ultimately want to be able to express the area of the cross section in terms of y. And so the volume here is really equal to the integral of pi times AB dy, but we don't know what A and B are in terms of Y yet. So that's why we have to use these similar triangles, is we need to be able to determine like, how do we write B in terms of Y? How do we write A in terms of Y as well? So let's determine what A is going to be in terms of Y. So we have this picture of a triangle here. So I'm just rewriting this triangle I have written in orange outside of the cone, so we can see what's going on here. So we have this orange triangle whose base is given by 6. And then the height of this triangle is given by 12. And then inside of this triangle, we have a purple triangle. The base of this triangle is given by A. And then we're going to assume that the height of this cross section is Y. So like the height here is Y, which then implies that the height here is going to be 12 minus Y. So the height of this triangle is given by 12 minus Y. And so these two triangles are what are known as similar triangles. So their side lengths are proportional to one another because we have this triangle lies inside of this larger triangle. And so what the similar triangle idea allows us to do is it allows us to equate the ratios of the side lengths of each triangle equal to one another. So we use similar triangles. And then using the similar triangles, what this is saying is we can set like the ratio of 12 over 6, so the height over the base. We can set this equal to the height over the base of this smaller triangle. So we have 12 minus Y over A. And so this is really saying that we have 2 is equal to 12 minus Y over A. And again, our goal is we want to write A in terms of Y, right? So you just solve this equation for A. And in doing so, you get 2A is equal to 12 minus Y. You can divide both sides by 2 to get that A is equal to 12 minus Y over 2. Okay, so that's the first part. So does anyone have any questions in terms of how we found what A is going to be in terms of Y? It's the height of the cross section. So it's the distance from the bottom of the cone to the cross section that we have here. So the reason Y is important is depending on what your Y is going to be, the area of the cross section is going to vary. So for small values of Y, the area is larger. For larger values of Y, it's smaller. So like as Y changes, the area changes. So this is why we have like this variable Y that shows up. It's not a constant. Okay, any other questions about finding A? And then for B, you do the exact same thing over again. So I'm going to do it in maybe a little bit less detail. We had this other triangle, this blue triangle here, the base of which is 4, the height is 12. So the height of this is 12. Then we have this smaller triangle inside of it, whose base was given by B. And then the height, again, is given by 12 minus Y. Right, so I'm looking at this triangle now that I'm highlighting in red. Right, so you just do the exact same thing over again. So by similar triangles, we have 12 over 4 is going to be equal to 12 minus Y over B. And then you just solve for B. So you get B is equal to 12 minus Y over 3, or over 4. No, over 3. Just doing the exact same thing over again, right? And so now we take this volume equation. So we have the volume. This was equal to the integral of pi times AB. This is exactly what I had written before. And if we want to find the volume, it's going to be a definite integral. And so we're integrating with respect to Y. So the limits of integration are going to go from 0 to 12, because that's the total height of our cone. So this goes from 0 to 12. And then you just plug in the two values that we found for Y. So this is pi times the integral from 0 to 12. A was equal to 12 minus Y over 2. And then B was equal to 12 minus Y over 3 dy. And then you can go about solving this integral. On the exam, I'm just going to ask you to set it up. You don't have to compute it, so you can leave your answer like this. Like if you want to compute this, you just bring out a 6, so you get like pi over 6. And then you do 12 minus y squared. You get a polynomial, you use the power rule. It's kind of boring. So I'm just gonna stop here. The interesting part is the setup, and that's all you'll have to do on the exam as well. So I'm just gonna stop here. Okay, any questions about setting up this volume integral? Yeah, question.
Can you do it like differently? Like, should it's maybe you find like A in terms of B, just do it in terms of
You probably could. I don't know exactly how that would play out. Like if you find a way to relate A and B with one another, and then you can relate A to Y, then that tells you can write B in terms of Y as well. So you could do something like that. I'm not exactly sure how that would play out, or if it would be like easier or harder. But if you see a way of doing it and it's valid, then you can do it. Is what I would say. There's probably more than one way of going about this, but I think the similar triangle idea is pretty intuitive. Any other questions about this problem? Yeah, question.
how do you set up A
Oh.
and B? Like if I switch B with A and A with B, how do they know like who's that with B?
It doesn't matter. Like at the end of the day, we're just multiplying the two things with one another, and the order of multiplication doesn't matter. Yeah, so it doesn't matter. Like if you said this were A and this were B, you'll get the same answer. Yeah, question in the back. Oh yeah, before I do that, are there any other questions about this problem? Yeah, question.
Why are you multiplying A and B together?
Yeah, so the reason we're multiplying A and B is that the area of the ellipse is pi times AB. So if it were a circle, the equation would be pi r squared. So inside of the integral, you would have like a pi, and then you would have like an r squared inside of here instead. It's all just dependent on whatever shape you're given at the end of the day and the area equation that's given to you. So that's why we're multiplying A and B with one another. Okay, any other questions about this problem? Okay, so do problem, you wanted to do 14? Yeah, we'll do problem 14. Okay. Yeah, so for this one looks scarier than it actually is. And I guess like our only experience with reduction formulas was that like horrible like trigonometric integral, but not all of them are so bad. So for this one, it wants you to derive the reduction formula where you're given an integral of a power of the natural log. And then after that, it wants you to derive or like find an equation to calculate, use the reduction formula to calculate this integral. And so whenever it asks you to find a reduction formula, you should be thinking like, I need to be using integration by parts here. And really, if you have a power of the natural log or the natural log, usually it means you want to be using integration by parts, unless U substitution works. So here we have the integral, this is 14a, of the natural log of x to the kth power dx. And so just like we did when we were finding the integral of the natural log, we're going to apply the same idea here. So when we're finding the integral of just the natural log, what we did is we let u be equal to the natural log of x, and we let dv be equal to dx, and then we just did the integration by parts formula. We're going to do the same thing here, even though we have a power of k, or a power to the natural log. So we're just going to let u be equal to the natural log of x times k, and then we'll let dv be equal to dx. And let's just see what happens. So if we take the derivative of u, we have to use the chain rule. So this is going to be k multiplied by the natural log of x to the k minus 1 power. And then you have to multiply by the derivative of the inside. So you have to multiply by the derivative of the natural log, which is 1 over x dx. So you end up getting this as your du. And then your your v is just going to be the integral of dx, which is just going to be equal to x. And so now if we use the integration by parts formula, so the integration of parts formula is you do u times v minus the integral of v times du. Our u and v, so we have the natural log of x to the kth power times x. So this is equal to x times the natural log of x to the kth power. And you can tell we're on the right track, because if you compare this, it's what we wanted to have here, right? So like we're on the right track, and then we just have to do the integral. Like we subtract by the integral of v times du. So v is equal to x, and then du is equal to k. times the natural log of x to the k minus 1 power times 1 over x dx. And so we have an x here multiplied by a 1 over x, so those terms cancel out with one another. Let me bring this down here. So we end up getting this is equal to x times the natural log of x to the kth power minus k times the integral of just the natural log of x to the k minus 1 power dx. And you can see this matches exactly with the formula that we wanted to derive in the first place. So we found that the integral, the kth power of the natural log of x ends up being x times the natural log of x to the kth power minus k times the integral of the natural log to the k minus 1 power. And so the reason why this is helpful, or why it's called a reduction formula, is we're taking an integral of the natural log of x whose power is k, and then we're translating it into an integral where the power of the natural log is k minus 1. So we're reducing the power by 1. And if you do it enough times, eventually this integral will just be a constant. So it makes life a lot easier. Okay, any questions about 14a? Yeah, question.
Something like this possible to show up on the exam?
Yeah, I mean, if it's on the review, then it's possible to show up on the exam. Yeah, but I mean, it shouldn't scare you. Like, I'm really just going to ask you, like, and really it is just like, I'm asking you to do integration by parts, right? And then I show you what the answer should end up being at the end of the day. So, like, this shouldn't be too scary. Any other questions about A before doing B? Okay, so for part B, you just have to use this formula a couple of times to reduce this power of natural log of x to the third power to something that's easier to compute. And so we just make use of this formula. So I'm going to write out, let's just write out the full formula here. Yes, this was k minus 1. So this is the integral of the natural log of x to the kth power dx is equal to this thing. So for B, it wants you to use this formula a couple of times. So we want to find the integral of the natural log of x to the third power dx. So in our case, our k is equal to 3. And so the first, and using the like this reduction formula, this tells us that the natural log, or the third power of the natural log, if we take the antiderivative, it's going to be equal to x times the natural log of x to the third power minus 3 times the integral of the natural log of x to the second power dx. So again, I'm just applying this formula we derived from part A, just letting k be equal to 3. So the k here becomes 3, k minus 1 becomes 2. And then you have to apply the reduction formula to the natural log of x squared. So this is the same thing as doing x times the natural log of x to the third power minus 3 times the integral of the natural log of x squared. So the natural log of x squared, again, if you plug it in to this formula, we have k is going to be equal to 2. So this is going to be equal to x times the natural log of x squared minus 2 times the integral of just the natural log of x dx. And then the final application. So if you want to determine the integral of the natural log of x, you can just remember we did it in class. It's x times the natural log of x minus x. But you can also just use this reduction formula if you want to. So this is x times natural log of x to the third power minus 3. I'm just going to leave everything in this form. Natural log of x squared minus 2. And then the derivative or the integral of the natural log of x. You can use the formula here. So in this case, k is equal to 1. So this is going to be x times the natural log of x minus the integral, or minus, just minus the integral of the natural log of x to the 0th power. So that's just 1. So that'll be minus x plus c. So if you want to like expand this out, you should end up getting the following. So it's like x times the natural log of x to the third power minus 3x times the natural log of x squared plus 6x times the natural log of x, and then minus 6x plus c. You can leave it in either form. I don't really care. But it's just a matter of, you just apply this formula over and over again, right? So I'm just making substitutions. I substitute in like k is equal to 3 into this formula, and then you do it for natural log of x is equal to 2, and then you do natural log of x where k is equal to 1. Okay, I would say this part is less likely to show up on the exam, but I would say the possibility is non-zero, so you should know how to do this. Yeah, any questions about this one before moving on? Yep. Yeah, we'll do number 11 next. Before we do number 11, any questions about this part? Okay, next is what's number 11? Okay, so for number 11, it wants you to find the volume of the solid attained by rotating the region, closed by x squared plus 6, and then 8x minus 1. Let me write it down. So I need more space for this one. Okay, so we'll just do it underneath here. So this is problem 11. I'll write down the problem just so that way I know what's going on. So for 11, it wants you to find volume of solid obtained by rotating region closed. Okay, so we have the following functions. We have y is equal to x squared plus 6. And we have y is equal to 8x minus 1. And then we're rotating about the x-axis or about the y-axis. Okay, so what we want to do here, I like just drawing the pictures to make sure we understand what's going on. So we're going to have the following graph. And the axis of rotation is going to be the y-axis. So I'm going to draw like this little arrow here to denote this is what we're rotating about. And so I guess like the first thing you generally want to do here after drawing the axes or maybe before is you want to find the point of intersections between the two curves here. And so you're going to set them equal to one another. So we have the following intersections. So we have x squared plus 6 is equal to 8x minus 1. And then we just solve for x. So this is the same thing as having x squared minus 8x plus 7 is equal to 0. And this is the same thing. You can factor the quadratic in the following way. So this is the same as x minus 1. And then x minus 7 is equal to 0. And so this tells us the points of intersection are going to be x is equal to 1 and then x is equal to 7. And so that tells us the interval in which we're going to be integrating over, right? So we have an intersection at x is equal to 1, an intersection at x is equal to 7. And so the picture kind of looks like the following. I'm not going to go into too much detail about like what the graph is. So you'll plug in numbers and kind of see what they end up looking like. So the line 8x minus 1 has like a y-intercept of minus 1. So it's going to look something like this, give or take. It's not perfect, but we just need like an intuition. And then the other is a parabola, x squared plus 6. So it ends up looking something like this. And so this is the region we're going to be interested in. I mean, at the end of the day, you just have to realize or understand which function is above the other on this interval from 1 to 7. So you don't even really have to graph this if you don't want to. You can just know, like you can plug in like x is equal to 2 and you'll see that 8x minus 1 is greater than x squared plus 6 at x is equal to 2. Right, so this is, so it's up to you. So this is 8x minus 1 is a straight line, and then we have x squared plus 6 is the parabola. And so it wants us to find the volume of this region rotated about the y-axis. And so if we're rotating this region about the y-axis, what method are we using? Yeah, it's going to be the shell method. You can just think in terms of, and this is a useful thing to draw. You usually want to choose like a random value x between 1 and 7. And you want to think about what the cross section is going to look like. So because the cross section is parallel with the axis of rotation, we should be using the shell method. And you can also think in terms of, we have functions in terms of x, and we're rotating about a vertical axis, so it should be the shell method, however you want to think about it. And so the shell method, when we're thinking about the shell method, we should be thinking in terms of circumference. So the equation is going to look something like this. So we're going to have that the volume is going to be equal to 2 pi times the integral from 1 to 7, the 2 points of intersection. And then again, thinking in terms of circumference, we should have something, so we have like a radius, and then we have a height, which doesn't really relate to circumference, but I'm just gonna write it down as height anyways. So you should be thinking of the radius. The radius is the distance of some arbitrary cross section with your axis of rotation. In this case, it's just going to be x minus 0. So maybe it's a little wacky writing it like this, but I'm going to do it anyways. So this is 1 to 7. The radius is going to be x minus 0. So again, it's the distance between your arbitrary cross section and then the axis of rotation. So it'll just be x minus 0. And then the height is just going to be given by whatever your upper function is subtracted by whatever your lower function is. So in this case, this is going to be 8x minus 1 subtracted by x squared plus 6 dx. And so if you write this out, this is going to be 2 pi times the integral from 1 to 7 of x multiplied by minus x squared plus 8x minus 7 dx. And then if you integrate this, I'll write out what the integral ends up being, because I don't want to go through like all the algebra. So it ends up being 2 pi times minus x to the 4th over 4 plus 8 over 3 times x cubed minus 7 over 2 x squared. Evaluated from 1 to 7. If you really want to know what the number ends up being, it's 288 pi. But again, on the exam, I'm just going to be interested in making sure you know how to set up this integral in the first place. Question?
For the most part, is the shell method, is it always just x for the radius for the most part?
I mean, it just depends on the axis of rotation. So if we were doing like x is equal to minus 2, then it would be like x, like this distance would be x, but then this distance is 2. So it'd be like x plus 2 would go in for this part. And if we instead had something like x is equal to 8, right? If this were 8, like x is equal to 8, then the radius would be 8 minus x, right? Because like this is 8 here. The distance from like this x is equal to 8 to this x value here is it going to be like the larger number subtracted by the smaller number. So it'd be 8 minus x. So it's something you have to be careful about. Like it's going to change depending on your axis of rotation. It was equal to 0 just because we were going about the y-axis. So like x is equal to 0. Any other questions about 11? Oh, do you have a question? Yeah. Oh, scroll up or down. Yeah. Yeah, and again on the exam, there's going to be a number of problems where I'm just going to ask you to set up the integral. I'm not really interested in going through like the total computation. So I'm just really interested in making sure you know how to get this integral in the first place. Yeah, Hannah.
Would there be like a flow rate question?
Oh no, nothing on the flow rate. Yeah, I don't think there's a flow rate problem on the review, is there? Yeah, I don't really care about flow rate that much. You don't have to know it. Any other questions you want me to go over from the review? If not, I'll choose some, or let's see. Yeah, so we did an integration by parts 1. What else? There's a total mass one. Let's do some integrals. We can do let's see, what would be a good one? Let's do more integration by parts because we haven't had that much experience with integration by parts, and it shows up a little bit on the exam. Let's do M. So for M, this is probably the trickiest integral on the review. So for this one, we have the integral of the natural log of x over x dx. So this is similar to a problem we did in class yesterday or during the group work yesterday, where you kind of want to do a u substitution before you do an integration by parts here, right? Because it's kind of like if you wanted to straight up just use integration by parts, it's kind of hard to tell like what your u is going to be and what your dv is going to be, especially because we have like a natural log instead of a natural log, or a natural log inside of a natural log. If you took the derivative of this, it would be a mess, and I don't know how things would really work out. So we're going to begin with a u substitution. So we'll let u be equal to the natural log of x. So then du is equal to 1 over x dx. And so you can rewrite this in the following way. So in this case, du is 1 over x dx, and we have a 1 over x dx inside of the integral already. So this is just equal to the natural log of u du. And so you could just remember what the integral of the natural log of u ends up being equal to. But it's also good to know how to find what the equation is going to be in case you don't have it memorized or it's not written down. And so if you want to find this integral, you want to use integration by parts. So we already used u once. So instead of doing uv, I'm going to write w instead of u. So I'm going to say like w is equal to the natural log of u. Then I'm going to say that dv is equal to du. So now if you take the derivative of both sides, or derivative of both sides of this, you'll get 1 over u du. And then for v, you'll just get that this is equal to u. And so this is going to be equal to u times w. So it's going to be u times the natural log of u minus the integral of v times dw. So v is equal to u, dw is equal to 1 over u du. So you get u times 1 over u du. These terms cancel out with one another. And so this integral just ends up being equal to u times the natural log of u minus u plus c. And then you just need to plug in what we originally had for u here. So this is going to be equal to the natural log of x being multiplied to the natural log of the natural log of x minus the natural log of x plus c. Right, so this one, it's kind of a combination. Like it helps to do u substitution first. After doing u substitution, you end up getting the following integral. And then to compute this integral, you want to use integration by parts. Okay, any questions about this integral? Yeah, question. We already used u once when we were doing u substitution, so I thought it'd be weird if we wrote u again, because then we'll be having like u is equal to the natural log of u, which doesn't really make sense, right? Like, yeah, it just get too messed up. So I used w instead of reusing u over again. Yeah, question. Which one? Oh, I. Oh yeah, I's a good one too. So this is probably the last problem I'll do. I don't think we'll have time. So for I, is it okay if I erase this? Does anyone want me to keep it up? I mean, I'm sending out solutions in a couple hours, so you'll see this anyways. But okay, so I'm going to erase this just to make space. Okay, so for I, we have the following. So we're doing the integral of 1 over t times 1 plus a natural log of t squared dt. And so for this one, it's kind of like, we haven't really talked about inverse trig functions that much, but the two ones to remember are like how to get, like what integral ends up being inverse tangent and which integral ends up being inverse sine. And so for this one, it kind of looks like, ignoring the 1 over t, we have something of the form of like 1 plus something squared, which kind of makes it look like we have something of the form of like 1 over 1 plus x squared, which we know is inverse tangent. And we also note that we have a natural log of t, and if we take the derivative, we get a 1 over t. So let's just see what happens if we let u be equal to the natural log of t. So this is equal to 1 over t dt. And so if we do u substitution, substitute everything in terms of u, it transforms into something that we know. So this is the integral of 1 over 1 plus u squared du, right? Because we have this 1 over t dt. This is just equal to du. And then natural log of t was equal to u, so you just get 1 over 1 plus u squared. And so this is just equal to inverse tangent of u plus c. And then you just plug in back into the original variable. So this is going to be inverse tangent of the natural log of t plus c. So this one is just a matter of using u substitution and then recognizing that we know what this integral is in terms of inverse tangent. Okay, any questions about I? Okay. Are there any other questions people want me to go over before ending class? Yeah, go ahead.
How long does it take for 12?
Oh, I passed it. Oh yeah, 12 would take a bit of time. I can do the first part of 12, or at least I'll set up the first part of 12. So for 12a, I'll go through it a little bit faster. So we're looking at the following. We want to find the volume obtained by rotating the region A below about the axis y is equal to 6. So we're rotating about this region right here. So this is our axis of rotation. And so we're rotating about a horizontal axis, right, in our function, or like the functions are in terms of x. So we should be using the washer method here. And so for using, this one looks a little bit weird to draw because like if you look at the cross section here, right, this is going to be like 6 minus like x squared plus 2. But we also have like the axis of rotation is 6. So we have like 6 is on top of this curve y is equal to 6, which makes it a little bit weird. And so what ends up happening, I'll just write it out. The outer radius here. So this is the distance from our axis of rotation to the curve here. This is given by what I already have written, actually. So this is just going to be equal to 6 minus x squared plus 2, which is really just equal to 4 minus x squared. And then what's weird about this is the inner radius. So the upper bound of the pictured region is y is equal to 6, and it's also a region of rotation. So the distance, or like the inner radius, just ends up being 6 minus 6, which is equal to 0. And so what the integral is going to end up looking like, so the volume, again, we're using the washer method here because we're rotating about a horizontal axis. The cross section is perpendicular to the axis of rotation. So this is going to be pi times the integral from 0 to 2 of the outer radius squared. So this is going to be 4 minus x squared squared. And then you subtract by the inner radius squared. But the inner radius is just 0. So it's going to be 0 squared dx. So then you compute this integral. It's 9:48 now, so I'm not going to do that. But you just compute this integral, and that'll tell you what the volume is. And again, I'm just really concerned about, like, you know how to set up the integral on the exam. So this is definitely one that you should go through on the review. But yeah, I'm gonna stop there. Any questions before I conclude? Yeah. We're integrating with respect to x. So like on the x-axis, we're going from x is equal to 0 to x is equal to 2. Yeah, so I'll post these after I'm done teaching my next class. So around like 11 o'clock, between 11 and noon.